Hi all, welcome to part 10 of the video lecture on counters. See, what we discussed so far is regarding counters, and the last part of the video we saw something called the synchronous counter, right? In part 8 onwards we started discussion on synchronous counter, and we taken a particular case study like how to implement that synchronous 3-bit binary counters. That is what we discussed in the last video in part 9, I think. So 3-bit binary counter, right now you already know how to implement it in a asynchronous way. Now in the last video how to implement it in the synchronous way. So both are clear, right? Synchronous way means all the flip-flops are triggered by a common clock, something like this. And so the procedure we followed is like we come up with the state table, right? State table containing all the input combinations. State table. Okay, so for example, at any time, suppose the flip-flops they are so the bits are like A2, A1, A0, right? If the bits are like say 101, then after applying one clock pulse, something like after the rising edge of the next clock pulse, you know, this A2, A1, A0, the states are getting changed, like after 5 the next state should be 6, right? So that is counting because we are talking about a binary counter, by default a binary up counter, right? So this should be the change needed. So accordingly we derived what could be the T input for the flip-flop that corresponds to this bit A2, I mean for this one. So this is our TA2. What is this TA2? What is this TA1? And what is this TA0? So like that we derived, and we saw that for A2 the bit remains same, right? Is after the clock pulses. So for that the input should be 0. So toggle flip-flop, right? So if I am giving 0, it will return the last information. Similarly for TA1, the bit is toggling, right? From 0 it is toggling to 1, so that the input should be 1, then only the toggling will happen. And similarly the last bit is also toggling, so that this TA0 should also be 1, then only that toggling will happen. So like that for every state transition we saw what is this TA2, TA1 and TA0, and then we simplified an expression for this these three inputs, and we found that as a function of the current state A2, A1, A0, what could be your TA2, TA1 and TA0. So that is what we derived, and we saw that this TA2 is nothing but A1 and A0. Okay, so that is what is implemented like this. So here we have A1 here, right? This A1 is connected here, and here we have this A0, and when you are performing A1 and operation with the A0, you will get the TA2. Similarly we derived like using KMAP, we saw that this TA1 will be something. So what is your TA1? That is nothing but this A0, right? You can see that so this connection is coming for A0, so this should be A0, and finally this TA0 is simply 1. So because in the truth table, I mean in the KMAP we saw only for all the entries are either 1 or the don't care, so we grouped it into a single what called cubic shape, and where we derived it like 1. So it is always true like that, because you know the least significant bit it will always toggle, right? During counting, if you are looking at the up counter, so it will count like starting from 0 0, it will go to then 0 0 1, then 0 1 0, like that 0 1 1. If you are looking at the least significant bit, it is always toggling. So that is why the one which is controlling the least significant bit is this flip-flop 0, right? So for this flip-flop 0, the corresponding input should be 1, because I want it to be toggled all the time. Similarly this is our flip-flop 1, and this is our flip-flop 2. So like that we are having 3 flip-flops. Okay, so for implementing a 3-bit counter. Okay, so basically it's a 3-bit register only which is going through a predetermined state like that. Now what about the bit that is A1? So A1, you can see that A1 is the TA1, I mean the toggling should happen corresponds to A0. So A0 is connected as TA1. So what will happen initially, you know, so this bit is 0. So whenever I am having a 0, it will retain the last information like this. So this is your A0, this is your A1, and this is your A2. Okay, so we are looking at A1. So if we are looking at A1, when we need that toggling, so we need toggling corresponding to the case when this A0, because this the input to this A1 TA1 is A0. So whenever this A0 is equal to 1, this bit will toggle like this. Okay, so so otherwise if that bit is 0, it will not toggle, it will simply retain this one. Okay, similarly this is 1, so definitely this bit has to toggle. Okay, and this will the least significant bit will toggle always. Okay, and now what about the last bit? So last bit is determined by A1 and A0. So the thing is that just look at the um, bits that are following it. So here you can see, so I ask you to find some trick on it, like if for 3-bit case you can depend on the state table, fine. For 4-bit also, if you want 16 entries will be there, you can check it, you can come up with the circuit using this kind of a logic. But what about 5-bit and 6-bit, 8-bit, like that? So that time if you can have some observation beyond the straightforward method, that will help you. Okay, and the observation is something like so if I am having 3 I mean A0, A1, A2 some 3 bits counter if I am having, this is how I am controlling the input. Suppose I have a 4-bit counter, 4-bit binary up counter, then you know this TA0 will be there. What is TA0, what is TA1, what is TA2, and what is TA3, like that you have to find out. Right now what I was saying is this TA0 will be 1 because the least significant bit will always toggle, and similarly this TA1. Okay, so you have to find out all those things. What is this, what is this bit, and what is this? So this has to be 1 always. And what about this TA1? It should be A0 just like before, because whenever this A0 bit is 1, I want the other bit to be toggled like this. Okay, so like this. So whenever this current state of this A0 is 1, on the background what is happening, on the background 1 means a 0 to 1 transition just happens, something like that. Okay, so that the A1 bit should toggle. Okay, and similarly your A2 is just like before, it will be A1 dot A0. That means so let's see this count. Okay, so here the next one will be 1. Now here you can see that in this case both A0 and A1, both of them are 1 1, right? So both of them are 1 1, and that time I am toggling this bit. Okay, so the most significant bit is getting toggled when all the smaller bits are 1, something like that. Okay, so you can see that all the smaller bits are 1, and you know this is how binary works, right? So when all these bits are 1, these bits will toggle, and finally this will also toggle like that. So that is why this is like a A1 dot A0. This A2 is a more significant bit, and that is controlled by TA2, right? The flip flop 2 and the input is TA2. I want that TA2 in mode toggle mode, then only that A2 will switch to that one. So for that what I done is I taken that A1 and A0 and I pass them through a AND gate, and you know the speciality of AND gate, this will give you a 1 only when this A1 A0 both are 1, and both A1 and A0 are getting 1 only in this case, and that time only I want the next bit to be toggled. Otherwise if see if you are looking at this case or this case or this case, right, in all these 3 cases one of them is 0, so that the AND operation will give you 0, so that I don't want that toggling, I just want to retain the information, like that I will pass the information. But in this case both, so corresponding to this case, if you are looking, this A1 dot A0 is giving me a 1, so that I am asking this bit to toggle. Okay, so that is the idea. Now can you tell me what will be your TA3? Okay, so that is my question, TA3. So for understanding TA3 I just need, because now it is a 4-bit counting process, right? So let me take this example like 0 1 1 1. So can you tell me what is the next count? 0 1 1 1. The next count will be something like 1 0 0 0. Okay, so hope you get it, right? Why I am getting like this? So if in this case let me write like let the bits be 1 second. Okay, so we want to see what is this TA3, so that is why I am taking like this. So if it is a 4-bit counter, then the bits will be like A3, A2, A1 and A0, and I will add one more T flip flop. So that is the idea. And you know this T so what we have this information like TA0 is 1, so that will let this bit toggle. Okay, so TA0, because this is by default the least significant bit will toggle, because I am connecting 1 as the input to this TA0, because okay. And what about TA1? Okay, so TA1 is actually A0, and you know A0 is 1, so because A0 is 1, this flip flop will also toggle, and that will change this 1 to 0 again, and that bit is toggling. And now what about your TA2? TA2 is A1 dot A0. Now you can see that both A1 and A0 are 1. So that their AND operation will give you 1. Okay, so that makes this flip-flop toggle in the toggle mode, because TA2 is now 1, so that will toggle this A2 bit also, right? Now what about A3? And you know that A3 also you want to toggle, right? So how can you tell that? Because A3 will toggle only when A2, A1, A0 all these bits are 1. So that is a scenario. So how can you express it? Like A2 dot A1 dot A0. Fine. So whenever this 3 input AND gate, so now I need one more AND gate which is of 3 inputs. All the remaining bits, 3 least significant bits A2, A1, A0, I will be connecting to that AND operation, AND gate, and it will give you a 1 when all those bits are 1, and that will trigger this more significant flip-flop which I am adding at this point. This is my flip-flop 4, and for this I am getting this A3, what I was trying to say. So here this was your flip-flop 2. Okay, so fine. Now you know you can add. So how can you extend it to a 4-bit up counter? You add one more flip-flop and the same clock pulse you apply here also, right? Then what about this A3 bit? Okay, so this is your flip-flop 3, and this is your clock. Okay, and you know this. So here you have this TA2, right? Okay. Okay, so what I am trying to do is I am applying the clock like this. So this is my clock and this is my flip-flop 3, and from which I am taking this A2 as output, and here I need this TA3, and this TA3 I am saying like it is the so take an AND gate. Can you draw the AND gate? So you can draw this way, and the inputs to this AND gate are like one input is this one, because yeah, here you don't have to use a 3 input AND gate. Actually you need a 3 input AND gate, but already this A1 dot A0 is available, right, as this, so you can just take it. So 2 input is enough. Now what is the third input? I mean what is the next input? Next input is this this one, right? Like this A2 also you take and you apply here. Okay, I'm not okay. If you want, what you can do, you can draw like this. Oh. I'm just taking the connection from here, and from here, you know, without crossing things, I'm going like this. Okay, something like that. Okay, you got it, right? So what I was trying to take is A2 from here. So that A2, A1, A0, and this output I am connecting here. Okay, so you can see that this will give you A2, and finally this 2 input AND gate will now give you A2 dot A1 dot A0. So that I am connecting to TA3. So I want this bit to be toggled. Okay, so that is the meaning. So now you got the idea, right? Now you can generalize it for a 4-bit counter, 5-bit counter also. So for 5-bit counter it will be like there will be one more flip-flop you need. And what about your TA4? 5th bit. Okay, so what is this? What is TA3 and what is and what is your TA3, what is your TA2, and what is your TA1, and what is your TA0. Fill from the bottom, you know, this is 1 and this has to be A0, and this has to be A0 dot A1, and this has to be A2 dot A1 dot A0, and this has to be A3 dot A2 dot A1 dot A0. So every time one more input will come for the AND gate, and 2 input AND gate is enough, because already other least significant bits are getting ANDed by the previous AND gate. So like that you can connect, and it will work nicely. So this observation is important. Now you can implement this some k-bit binary counter easily, because you don't need to depend on that state table. So state table method is good provided you don't have any idea, but this kind of an observation and generalization using this is more important, because state table will be very much tedious and difficult to implement for some higher order circuit like a 10-bit circuit. And now you can go for any number of bits, right? Yeah, so that about it. So this generalization is what we needed. So synchronous binary counter, what observation we made. The design of a synchronous binary counter is so simple that there is no need to go through the sequential logic design process. That is what we done in the last part of the video. But from that only we understood this, right, after understanding the circuit. But from the sequence also you can may have this observation. So how these bits are changing, like from 0 1 1 1, how it is changing to 1 0 0. That observation you can have from this bits also, but still. Okay, in a synchronous binary counter, the flip-flop in the least significant position is complemented with every pulse. Okay, that is what we understood. That is why the TA0 we connected as 1. So the flip-flop in any other position is completed when all the bits in the lower significant positions are equal to 1. So this is very important, and this observation is a final observation that is helping us to have the circuit. When all the least significant bits following it are 1, that will let the bit which is I mean, if I want to know what is the status of the bit AK, I want, like, if A0 to AK minus 1, all the bits following it are all 1, that will toggle akth bit. So that is the idea. Hope you got it. So for example, if the present state is like a 0 1 1 1, next state will be 4, that you know, right? So how it is you are getting this 4? Similar 0 1 1 1 we analyzed. Just here they are talking about 0 1 1, and now you know, now it's very clear this bit will toggle, right? So this bit will change, and as this least significant bit is 1, this will toggle, right? Now these two bits together are 1, this bit will toggle, but this will remain same, because it's the bits following it are all not 1. If when you are passing these bits through AND gate, that will give you 0. So that is the case. So that is why A0 is complemented always. A1 is complemented because A0 is 1. A2 is complemented because the bits following it, A1 and A0, both are 1. A3 is not complemented because the present state is like 0 1 1, which does not give all 1 condition. So that is our requirement, right? So this is how you can implement the circuit. 4-bit circuit, same thing I also implemented, just like instead of T flip-flop that I used, because T flip-flop is something easy to visualize, that is why I take it. JK also you can take, but if it is JK, you have to give the input to JK, and only 2 inputs are allowed, just like a toggle. What is the condition for toggling in JK? Condition for toggling in JK, you know, because JK is nothing but both J and K. When you merge, you got this T, right? So same way, J equal to 1 and K equal to 1 together corresponds to toggle. Okay, so or on other hand, when it comes to T is equal to 1. So both are same, because T is nothing but J and K together, right? Similarly, J equal to K equal to 0. J equal to 0, K is equal to, so that corresponds to no change. Okay, on background this corresponds to T equal to 0. So this is the idea. And same way, okay, if you want, you can use D flip-flop also, because such variations we already seen. But this, by default in exam you can use the T flip-flop, that is easy, unless otherwise stated. If they are asking you to do in JK, you have to do like that. Yeah, now tell me, this is your A0, A1, A2, A3, like that, the 3 bits I just drawn like this, but here they are drawing in a vertical way and starting from the least significant bit, and this is your most significant bit. Okay, most significant bit. And you know that it is something like, here they are using something in addition, count enable. So whenever I am making this count enable as 1, this will start counting. Okay, so I am having one more extra control. Clock is there, definitely that will control the operation. So clock is something continuous in nature, right? So in between, if you want to stop counting, if you want to enable counting, you don't have a further control. So that is why we are having a separate line called count enable. So the idea is, whenever this count enable is equal to 0, I will not enable counting, so it will not keep counting. But whenever this count enable is equal to 1, it will start counting. So initially our hope you remember what was your J and K for the least significant bit. It should be 1, right? Because least significant bit should toggle always, and that one count enable is equal to 1 will enable counting, right? So that makes this 1 here and here, so that it will in the toggle mode. So this connection will do that for you. Now from the remaining bits onwards, you know, this A1 to the this is your J, yeah. So what we understood is, the J input for A0 and K input for A0 both should be equal to 1. So that is achieved, right? Now what about this J input for A1 and K input for A1, just like a T input for A1 from the previous one. So this has to be your A0. That A0, this is something like a TA1 we got at A0. Same A0 will play here also. Whenever this A0 is equal to 1, the toggling I need, right? So in addition to that, here we are using just this count enable also. So because count enable should also be 1, right? So that I can write like and this will be this is equal to A0 dot count enable. So we just added that count enable also in addition to. So previously it was just A0. Similarly, your JA2 and KA2 both should be what? A1 dot A0 dot count enable. Count enable will come in addition to what we've seen so far. The previous circuit only. Additionally, we have this count enable. That's all. Similarly, JA3 equal to KA3. Both should be equal to the least significant bits. Right now we are in A3, so A2, A1, A0, all of them should be 1, and count enable should also be 1. Okay, so that is the meaning of this kind of an AND operation. Fine. Similarly, what about other bits? So hope you got an idea about how this 4-bit synchronous binary counter is working. By default, synchronous binary counter, what I mean is synchronous binary up counter. Okay, so this up is by default, it is there. Okay, but in the exam, if they may ask you down counter, so that time they will explicitly mention synchronous down binary down counter, something like that. Okay, so here by default binary counter means up counter only. So now you can design 4-bit counter up counter, and you can generalize it for 5-bit, 6-bit or any number of bits. Now the idea is clear, right? Yeah, that about it. Now what else? Now you think about how to implement a down counter. And down counter, you just understand like how these sequences are going and what will happen in for subsequent sequence, whether it each bit, whether it need toggling or not, and accordingly how we can give the inputs TA1, TA2, etc., or J and K inputs of the corresponding flip flops. Okay, as a function of the current state of the flip flop. So that we will see in the next video. And one more thing you can think is how to implement a counter that is capable of doing both this up counting and down counting. You have to come up with a single circuit that can perform up counting and down counting based on some control line. Again, similar to this count enable, we can use a control line. Whenever that control line is saying 1, you can do say up counting, and whenever that control line is say 0, you can do down counting, or in other opposite order, whatever it is. You just want to do both operation, and it should be controlled through a control line also. So that is the idea. So that circuit also we need. So just think about a down counter, and after that think about a counter which can do both the up counting and down counting simultaneously, say using a single circuit, right? Yes, thanks for watching.